All right, so our goal for today is to say, okay, Riemann sum, limit, integral, connectable. So today is the last day we're really going to look at geometry to find area under a curve. So what we started with last Friday was geometry and different shapes for finding areas, and that's how we're going to end and reintroduce the definite integral today. So Riemann sums are always rectangles, trapezoids are always trapezoids, and definite integrals are going to be the area under the curve of the shape that fits it best. So it will make sense as we get there. The front page of your notes are like Riemann sum summary. So those are all of the directions that if you got asked to find a Riemann sum or a trapezoidal sum, those are what you would follow. The big idea is that the K represents the number of subintervals. So when we did our limit, we had K subintervals, so that K value was your subintervals. And then your delta X is that B minus A over A. And then there's just my Riemann sum picture. Just do that. All right, so this is the next big part. The definite integral as a limit. The definite integral as a limit. We already talked about this. You have the limit. Our textbook sometimes will go from P to N, but that just represents the vector or N. The f of x sub I is your height, and the delta x sub I is your height. Again, what this does, or the limit does, is create an infinite number of rectangles. So, and again, I already typed that blue part for you. All it means is that if a function is continuous, and we should know by now continuity matters for everything. If a function is continuous, then it is integratable. If a function is continuous, it is integratable. That is different than derivatives. Continuity did not imply differentiability. Differentiability implied continuity, but here continuity implies integratability. So again, if a function is continuous on a closed interval, then a definite integral exists. Now, the difference is that if a definite integral exists, if we have a sharp corner or a cusp, then I have to break my integral into multiple parts. So we may not be able to take integrals over an entire frame, we have to break them into multiple parts. And that's what we're going to look at today. So the definition of the definite integral says that the integral from a to b of f of x dx is equal to that limit. So limits and integrals, just like limits and derivatives go hand in hand, the limit represents the rate of change. The limit, as we have n subintervals and add them up, represents the area under the curve, which represents the integral. So a derivative is a rate of change. An integral is an area. A derivative is a rate of change. An integral represents an area or a total distance. It allows us to find position. So it's important to understand the parts of an integral. So the parts of an integral allow us to understand what each one represents. So the integral symbol is a summation symbol in a way. So the integral symbol is like an S for sum. You have an upper and a lower limit. These are also called bounds. They do not have to go from least to greatest. However, if they are switched and B is smaller than A, then you are finding the area backwards or in the negative direction. So it's like saying I moved forward, but you want to find my area backwards. So you're like watching me in reverse. So you take the negative of that or negate it so that it became positive. The function represents the height. The function represents the height. It is called the integrand. The function is called the integrand. Dx represents the width. We know dx to represent a differential, and dx tells you the variable of integration. Dx tells you the variable of integration. So just like we had dy dx, and we had implicit where we had dx dx, dy dx, we had dr dt, where we integrated with respect to time. You can integrate with respect to y. So when we integrate with respect to x, we're finding the area under the curve between the curve and the x-axis. If we integrated with respect to y, we'd be finding the area of the curve with respect to the y-axis. So that's why it's important to know, like, is it dy or is it dx? If it's dy, you have to solve like x equals blah, 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 not y. So let's make that one last connection before we move away from Riemann sum notation. You have the summation of n to infinity of f of x dx. Which of those does it represent? So again, you're looking for something to the fourth power. Well, that's all of them. Now you are looking for something whose delta x is equal to 2. So my delta x needs to be 2 over n. So that eliminates your a and c. And my starting point is at 3. So I need my 3 to be inside whatever is being raised to the fourth, and I need a 2. So 3 and 2, both inside. Here, my outside tells me that my B minus A needs to be 1. That 3 inside could be manipulated to down in front to match my one end over here. So that means I need a 3 to be multiplied to my variable inside. Thus A. Alright, so I said it once, I'll say it again. We can define the area under the curve as long as the curve is integratable, meaning it is continuous, and then we call it non-negative if we're talking in terms of area. So integrals can be positive or negative, area cannot. So an integral can be positive or negative, the area cannot. So it's kind of like velocity and speed. Speed is non-negative, but velocity can be either. Okay. So it says for each of the following examples, sketch a graph of the function, shade the area you are trying to find, then use the geometric formula to evaluate. So if you think of the curve 3, that is a constant. We are integrating from 2 to 9. So if you're finding the area under the curve and integrating from 2 to 9, what shape should I create? Yeah. So you want to find this using a geometric formula. So my geometric formula is the area of a rectangle so the area equals base, which is 9 minus 2, times height, which is 3, or 21. So what that means is that the integral from 2 to 9 of the function 3 is 21. What we're going to do next week is learn how to find that algebraically. The absolute value function we know has a corner. The absolute value function we know has a corner. So this is the case for if you were actually finding the integral of this algebraically, you would have to break your integral into 2 parts. The same way we're going to break the area under the absolute value curve into 2 triangles. So if you think about the curve absolute value, it is a V-shaped curve. The slope to the right is positive. The slope to the left is negative. If you are trying to find the area under that curve, you're going from -2 to 1. So that will create 2 triangles. So the area under the curve is 2 triangles. The triangle on the left and the triangle on the right. So the area of the orange triangle is 1/2 base, which was 1. The height is taking that base value and plugging it into your function. So absolute value of height at 1 is 1. So the area of the orange triangle is 1/2. The area of the yellow triangle is 1/2. My base is 2. My height is 2. So the area of my other triangle is 2. So the integral comes from the area from -2 to 0 of the absolute value of x dx, and adding to it the integral from 0 to 1 of absolute value of x dx. And that break comes from where you created both your shapes. Because that means the curve itself changed. So the total area, or the value of that integral, is 2.5. A square root function represents what curve? A square root function represents what type of shape or curve? Alright, let's graph our points. So it starts at -3. So what would be the value of that function at -3? Yep. And the value of that function at +3? So I know what it starts at and I know what it ends at. So maybe I need to find a point in between. So what's the middle of -3 to 3? So let's plug in 0. If you plug in 0, you get 3. Any idea what the square root of 9 minus x squared represents? Semicircle. Okay. So it is a circle of radius 3. Because circle formula is x squared plus y squared equals r squared. So we solved for y, but we only have the top half of the square root. If it was a negative square root, you'd have the bottom half, or the whole circle. So we have a circle of radius 3, aka a semicircle. So we're going to use the area of a semicircle to find the area under the curve. So area of a circle is pi r squared. So now I only have half a circle. So the area of a semicircle is 1/2 pi r squared. And again, it's important to know your radius is 3. So this is a circle centered at the origin. It goes 3 in all directions. So 1/2 pi 3 squared, or 9 pi. So again, that would also be the value of the integral. Consider the function f of x equals 3 minus x. So this is linear, y-intercept at 3 with a negative slope. So it says find the area between the curve and the x-axis. for x equals 4 to 8. So from 4 to 8, my area or my curve is entirely below the x-axis. So area itself does not exist. However, the integral value would. So the area does not exist because it's all below, but the integral would. So if you were finding the integral from 4 to 8 of 3 minus x dx, or that curve, what shape has it created? What shape has it created? What? There's 2 flat sides. Trapezoid. So that's the trapezoid. Here's your base. Here's your base. Here's your height. A little tiny segment. So area of that trapezoid is 1/2. Remember, my height is this piece here, so it's 4 units high. And my little tiny funky base has a height of 1. My other base has a height of. So, and if you didn't know, what could you do? Well, you could take 8 and plug it in here, right? So like my graph drawing obviously doesn't look the greatest, but you could take 8, plug it in, 3 minus 8 is 5. So you get half of 4, which is 2, 5 plus 1, which is 6. So we get that the area of that trapezoid is 12. So the area is 12 because area is innately positive. The integral is 100% below the curve. So it would be negative 12. It would represent a function moving backwards. And again, think about derivative. If a derivative is negative, then the original function is perfect. All right, let's evaluate. Oops, we just did that. How does it work? So that leads into what I was just telling you. Area is innately positive. However, integrals can be above or below. If an integral is below, then that area is to be considered negative. If an integral is below, that area is to be considered negative. Now the next one I really enjoyed. So for this one, we're going to look at the sine curve from 0 to 2 pi. So I'm going to draw the sine curve up on here, but then I'm going to translate it to the whiteboard. So think about sine, right? Sine of 0 is, yep, sine of pi is, sine of 2 pi is. So then the max and mins of sine occur at, yep, 1 and negative 1. 1 occurs at pi halves, and negative 1 occurs at 3 pi halves. So it's up, down, up. There's my sine curve. Looking at that, if the max, wow, that was terrible. If the max and min are 1 and negative 1 above and below, what would that translate to for area from 0 to 2 pi? If I asked you to find the area from the beginning to the end, what do you think it would end up being? Perfect. Because the area above and the area below cancel each other. So So if you did the entire integral from 0 to 2 pi, even if you didn't know what that space was, they would cancel. All right. So going back to this example, we are given that y equals the sine of 2x equals 2 from 0 to pi. We are given that the integral of the function y equals the sine of 2x from 0 to pi. So they gave you this. That's a given. That's what that statement says. How would that translate then for the integral of pi to 2 pi? So 0 to pi is 2. Pi to 2 pi would be what? I already hinted at this. The integral from 0 to 2 pi ends up becoming 0 because again, this translates into the integral from 0 to pi plus the integral from pi to 2 pi, which we know to be 2 plus negative 2, which is 0. So it's kind of like saying whatever the object moved forward, the object moved backwards. So it's like starting and ending at the same spot. Because remember, an integral represents the distance. The integral represents the distance traveled, not displacement. Displacement is your total number of steps. Distance is how far you are from where you start. Okay. Given blah, 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 let's use this to evaluate the integral from 0 to pi halves. So if 0 to 2 pi is 2, 0 to pi halves would cut that perfectly in half, right? So we know it's symmetric. So therefore the integral from 0 to pi halves would be perfect. No. Negative pi to pi. So again, taking that into respect of a function, if you go to the left, negative pi, sine keeps its symmetry, so it's negative 2 and positive 2 again, therefore 0. Okay, what about 0 to pi? 0 to pi. However, what happened to my graph? It's shifted up 2 units. So now, my sine curve lives here. So its max is now at 3 instead of 1. And this 5 point is now at 2 instead of 0. So the area of this sine piece here has not changed. What's that area of that sine piece? It hasn't changed, right? It still remains 2. But now, what happened is that graph got shifted up and created this new area or this new space. So this would be what shape below the shape I already know. Yes, rectangle. So the height of the rectangle would be what you shifted your graph up, which is 2. The width of the rectangle is my upper and lower bounds again. It's 0 to pi. So from here to here is a length of pi. So area of a rectangle is base times height. So the base length is pi, the height is 2. So this integral is like the area of the rectangle plus the given 0 to pi of sine x dx. So you get pi times 2 plus the 2 that was given to you for that given integral. Therefore, this new area is 2 pi plus 2. Make sense? So that pretty much summarizes 5.2. 5.2 in your book is that Riemann sum limit and then the areas of the definite integral curve. So we did 5.1, this is 5.2. We'll do 5.3 and then probably have our mid-chapter fact test, just to give you like an idea of what's coming. So 5.1, 5.2, and 5.3 are really, really closely related. In 5.3, we actually learned the power rule in reverse. So like the easiest derivative was the power rule. We're going to learn the power rule in reverse for integration. And we'll talk about that next week when everybody kind of comes back on Tuesday. So on Monday, I just have like a quick like worksheet where we do like a few more shapes. And then I'll give you your big assignment today, so you have like all over Tuesday to do it. So it'll be like a little bit of textbook problems and then some AP classroom problems. It's been a while since we did AP classroom. I already showed you this. So I feel like one or two of the problems in the book say, check it on your calculator. But I showed you, we did this. This is how to find the integral on your calculator just to check it. So to check it on your calculator, you would just hit math 9 and then you enter the integral exactly as it's given to you on the problem. And I think that's all, like, I gave you the conversations to do that. So you can do some of this when you pick up.